All right, so good morning, students. Today we'll be coding another embedding called GloVe, which is another classic embedding, right, which is based on co-occurrences. By the way, a lot of students are trying to ask, like, okay, well, if we want to use Word2Vec, do we have to actually code that much? In fact, the quick answer is no. But what I'm trying to do is trying to teach using code from scratch, right? So you can fully understand the behind scene of Word2Vec, right? But in practice, you don't actually code from scratch. There's so many library out there that implement Word2Vec for you already, right? So I don't think there's a point in reinventing the view. But today we're gonna do the same for GloVe, right? And basically coding from scratch. All right. So today we'll be doing some load data, and we'll be reusing a lot of the code on the previous tutorial. And we will be building a co-occurrence matrix X. And this is the weighting function we talk about in the class, right? And we will have to write the code for preparing train data, and also a lot will be put on actually creating the model, the neural network. And at last is doing some training, plotting embeddings, and cosine similarity, which we already very familiar with this. All right. So without further ado, we're gonna first import our stuff. By the way, let me just restart my kernel. And now we import our stuff, and then on the load data, everything looks the same. We have the corpus, we tokenize, we numericalize, right? I'm sorry, we get the unique words, and then we numericalize. We append unc, and we have word to index, and we also have index to word. Right. The next thing we're gonna have is basically building a co-occurrence matrix X, right? And to do that is actually not so difficult, right? So firstly, we'll be counting the number of occurrences of each single word, right? Right, and we're going to call this xi, right? And then so this is the occurrences of each word. The next thing we have to do is basically counting the co-occurrence of two words given some window size, right? So in that case, I think what we have to do is maybe doing some skipgram, the thing that we did before, and that would allow us to later on count, right? So skipgrams. Sorry. And from doc encompass from I in range 1, like doc S1, right? And okay, 4, right? I'm not sure why I'm typing from. Maybe I'm thinking about importing. I'm not sure. And then center equal to doc I, and then the outside is doc I, and doc I minus 1 and doc I plus 1. And for each outside word in outside, we're going to append this one to this one. And what we want to append is basically the center and each out, right? So I think that is basically it. And then we're going to have a very nice skipgrams that. Then we can actually pass this into the counter. Counter skipgrams, right? And now I have some problem. It's a unhashable types list, right? Give me 1 second. Did I do something wrong right here? Okay. I should make it as okay. Once I make it as a tuple, then it can be counted, right? Okay. So now we have the counter of each of this pair and count as one. All right. Now what we're gonna do is we're gonna apply. We also will be preparing this weighting function, which is a very the idea is very simple, right? That is, if some words appear too much, then we don't want to have too much impact on the embedding, right? So this is just a simple weighting function. So so the definition, so we create a function weighting, and we're gonna input wi, wj, and xi. Okay. All right. And the first thing we will be doing is check whether the co-occurrences between the two words, which is wi and wj, is available, right? Maybe they don't have, right? Then we have to make sure that if not exists, then set to 1, right? So in that case, the reason why we have to set to 1 is that this is similar to something called Laplace smoothing, but this is actually not Laplace smoothing, right? But the idea is that even two words does not appear, it does not mean they will never be appear, right? So we just set to 1 as a minimum. In that case, for other pairs, we have to always add 1 more to make it 2, right? So that is just, and also it helps everything, the coding very stable too, right? So this is a common practice we do, right? And then what we have to do is set x max right here. The number of words that we don't want it to exceed, right? And here we're gonna set it to 100 in my code, right? And of course, we have to set some alpha, right? That is, how do we scale this function? What is this function, right? Which is just multiplying with some alpha. And then if co-occurrences does not exceed x max, then just multiply with some alpha, right? Otherwise, set it to 100. That's it. All right, and I'll set it to 1. Sorry, right? You can see that if it's basically x max, you just set it to 1. All right, so that is what this function return. All right, and then just return the weighting function, right? The weighting function, which is a number between 0 to 1. All right. Great. So now we're gonna do first this one. We're gonna say try xij equal to xik, and then we're gonna say wi and wj. All right, and xik is basically the co-occurrence that we have did previously before, right? And I think this is probably we'll be using this skipgrams, right? And then if yes, then we're gonna get the number, right? Which is basically this number. But if it does not exist, then we have to do something, right? Which is except xij equal to 1. All right. And then x max equal to 100, and alpha will be set to 0.75. All these numbers basically used according to the paper GloVe. And now we're going to just say that if xij it is less than x max, right? Then the weighting function is nothing but xij, right? Basically the co-occurrence, right, divided by x max. So you can see, basically what we are trying to do is that x max is 1, and other numbers is anything within this range, right? So to do that, we just divide by x max, and then multiply power to the exponent of alpha, right? Otherwise, if it's basically alpha, then we just basically, if it's x max, then we just set the result equal to 1. All right, and that is basically the weighting function that we want. All right. I think that should be it. Okay, and now we can write another function, right, which would be actually not the function, right, but basically giving me all the co-occurrence that we're going to be using in the prepared train data, right? So I'm going to first import something called intertruths, import combinations with replacement, and we're going to have this dictionary. This will be useful for keeping the co-occurrences, right? And then we're going to have weighting dic, right? And this is going to be something that after you basically it help us so this is basically something that already scaled, right, after you apply this weighting function, right? And so already scaled the co-occurrences using the weighting function. All right, and so now we can do something like this, and that is for bigram and combinations with replacement of vocab, comma 2, right? So let us take a look what this gives us, right? So basically, it takes all the vocab and it's a bigram, and it's just trying to give us all the possible bigram possible, right? And then what we're going to do is we need to have a co-occurrence of all this pair, right? And it will have some numbers, right? So to basically fill all the combinations. All right. So now we're going to say for if xi skipgrams dot get bigram, right? So basically, if the pair exists, right, in our corpus, we're gonna just get the co-occurrences equal to xik, and then bigram, right? And of course, otherwise you don't do anything. All right, and for the xik skipgrams of the bigram should be equal to co-occurrence plus 1, right? So this is again for stability, right? Remember that we want to keep track. We want to make sure that we always add 1, right? And then similarly, we also want to count for the opposite, right? So xik, xik, okay, sorry, this should be this. All right, because this is basically a dictionary that keep track, right? We don't want to modify this guy, which is a dictionary that we create up there, right? But this is the real co-occurrence matrix that we want to check, right? And then what we're going to do is bigram 1 and bigram 0, and I think this should be a tuple, all right, is equal to also core plus 1, right? So basically, apple banana should be also counted for banana apple. So the order should not matters, right? So this xik will be handling all the occurrences for us. All right, and so we're gonna keep doing this, right? And finally, we're gonna have something that looks like this, right? So we can actually print it out and take a look, right? So we're gonna have apple fruit 2, fruit apple 2, right? Apple banana 2, banana apple 2, right? So they should be equivalent, right? Because they are they basically the same, right? And we're gonna have all the pairs. All right, so now that would be something we want, right? But another thing that we actually want is the weighting dict, right? That is after we apply the weighting function. So what we're gonna do is the weighting dict, right, of this bigram. Sorry, of this bigram is basically applying the weighting function. And this weighting function take wi, right? That is bigram 0 and bigram 1, right, of the second pair. And then we're gonna input xik, right? And so this xik is basically having all the information about co-occurrences. And then similarly, we have to do for the opposite direction. So we're going to say bigram 1 and bigram 0 equal to, we're going to copyright this one right here. We'll do that, 1 and 0. And that should be it, all right? And we're gonna try to print this out, right? So so once we see this, this looks like a huge list, right? In which there's a probability of almost all the pairs, right? Oh, right, unk and fruit, right? The reason why the reason why we have this is because we take all the bigrams, and even the doesn't exist, it will pass, right? But it will try to do this anyway, right? And xik doesn't exist, but even that there will be still some probability, right? So you can see these are the words that actually appear in the corpus, so the probability will be a little bit slightly higher. But for those that also not in the corpus, they will be also having some probability, right? And then it will be very stable. When I say stable, for example, if you try to divide this probability, then if it's 0, then it will be divided by 0 errors, right? But by scaling this, it will be very nice. But because we scale this up, we also should scale this up by one more, right? All right, great. So I think we got this nicely done. All right. And I'm not gonna print this out to save a lot of space here. All right. And now we got everything nicely done here. So we're just gonna collapse this. All right. And we're also gonna collapse basically the co-occurrence matrix. All right. And we're gonna start preparing train data. And to make sure, I'm gonna just force it to stop here. Gonna clear output, restart, run all. All right, great. So everything run nicely. So the next part, what we're gonna do is preparing train data, and a lot of here will be similar to what we have done previously, right? So we're gonna first create this function, right? So I'm gonna first import a math function, and then by the way, let's clear out the errors, and then we're gonna create this random batch, right, function that can generate batch for me. And what we need is a batch size, word sequence, and skip grams, xik, and the waiting date. All right, and now we can now basically there's several things that we have to do, right? So convert our skip grams to ID, all right, using word to index, right? And then just randomly choose index, right? Choose indexes based on batch size, right? And then now we just get the random inputs and labels, right, based on this indexes. I think this is what we already did, right? And then make sure that we also have the co-occurrences of all the input and labels that we have, and also as well as the weightings, right? So we want to return a lot of things right here. We want to return definitely the X, right? We call this random inputs, and we want to return the random labels, right? But in extra, we also want to return the co-occurrence. Sorry. And we also want to return the weighting, all right, of that batch. That basically the weighting that belongs to that batch, right? Okay, so I think we can do this now, all right? So we're gonna do something like this for skip grams in skip grams. All right, and this one should be skip gram. All right, so let us recall what is this skip grams, right? So skip gram is basically the pair that we have, right? So for each of them, I'm gonna get the first one and the second one, and then just convert them into ID, right? So there will be a pair. So what I'm gonna do is a word to index of their first word, right? And sorry, I think I forgot. And then a word to index of the second word. skipgram 1. All right, and I think this should be that. All right, and now so we have a nice tuple, right? Based on that, which is already indexed. And I call this a skipgram ID equal to that. All right, so that would that is quite straightforward, and then we have to randomly choose indexes, right? Which is simply random index equal to np.random.choice, right? And then we're gonna just choose whichever skipgrams we have, right? So we're gonna say range length skipgrams ID, and according to batch size, right? And then replace equal to false. Okay, so now we can now randomly choose all this skipgrams and choose it as input and labels for us, right? And now we can get the random inputs, right? But before anything else, why not we declared some lists so that we can work with the random inputs, random labels, random COC, concurrence, random weightings. I think this is the name I gave. S. Okay. Equal to. Okay, great. We have 4 of this, right? And I think this should be fixed. Okay. All right. Now, so we're gonna say for index and random index, right? So this is so basically what I'm trying to do is we randomly pick a batch number of index from the skipgram ID, and then we just loop each of the index, get the input, put it inside random inputs and random labels. At the same time, also make sure we keep track of all these numbers for each of the input. All right, so now we're going to say random inputs dot append skipgram ID index the first guy, right, which is a center word, and then we're going to also have labels, and this one is 1, right, which is basically the outside word. All right, so I think we are quite good right here, and now we need to get the COC, which is the co-occurrence of this skipgram thing, right? Yeah, for those who don't understand currently what I'm doing, I would say you pause my video and let's just print this guy out, right? And you will be very clear what is happening right inside here. But I think it's it should not be that difficult. Yeah. And a pad equal to skipgrams index. All right. So so by targeting that, we will have some pair, right? So for example, this looks like, and then something like that, right? This is just an example. And then once we get the pair, we're just gonna try whether this have something, right? So COC equal to XIK pad, right? And this XIK is basically pass-in, right? And I guess this is the XIK skipgram that we're gonna, or maybe basically the XIK we have in up there. Maybe we can try to print this XIK and check how this look, right? Yep. So this is a XIK, right? All right, and then of course we have to anticipate that it doesn't access, right? So in that case, like we said, it's going to be 1, right? And then now we're just going to say random.coc.append. Mat, so COC, right? And of course, this COC is will be append, right? But what we're going to do here is we're going to apply mat.log right here. Right? And the simple reason is because later on we'll be using mat.log here, right? If you take a look right here, there's this log in front of the xij, right? So I just mat.log right away so that it's going to be simple, easy to use in the future. All right, and the next thing, so we have this random works for all the pad, right? And at the same time, we'll be also having the weightings. All right, and so the weighting is basically equal to, we can look up the weighting dict of this pad. All right, and we don't have to try anymore because this weighting dict basically have all the pair all the possible pair, right? And then we're gonna say random weightings that append and weighting. All right, so yeah, it looks very very neat. And so what we are trying to do is simply randomly choose something, and then just, I think this is basically just getting the X and Y, but right here we make sure we always get the co-occurrence of the pair, right, that we have, and then and also the weighting dict, right? But why not we just test the method and then take a look at whether it really works, right? So we're going to do batch size equal to 2 and input. We're going to say call XY COC and weighting equal to random batch. And what it does, it need is a batch size. What does it need? Word sequence. Word sequence is basically the corpus. And I think the next thing it needs is the skipgram, which we already have. And then the next one is XIK. And XIK is basically the XIK. And then the weighting is basically the weighting dict, right, that we have defined earlier. All right. So now, once we have that, we can check a look at X, right? So X is basically, this is the center word, right? And then the Y is basically the outside word, right? So 4 is a map with 2 and 5 is a map with 2, right? Of course, if you're wondering, you can always try index to word 2, right? And then that is apple. And for that one, index to word 4, that would be basically banana to apple, right? So that would be an easy way to make sense of what is happening here. Okay, but anyway, we can now print the COC, right? And this is basically the co-occurrence of 4 and 2, and this is the co-occurrence of 5 and 2. Notice that this is not a number because we do a mat.log right here. But mat.log is a monotonically increasing function. So it does not matter. If it's big, it will be big relatively. And then the weighting, right? So this is the weighting of this pair. All right. So I think that is the prepared train data. And I will be grabbing some drink first, and then I will be back. Give me 1 second. All right, so now I think we're done here. So we can close this one and work on the model, which is the last part we're going to do, right? So based on the GloVe derivation, right, we have to take two words, dot product, plus some BI and plus some BJ. BI and BJ is not really, does not really matter, right? But what we want to do is minimizing the distance between the dot product of two words and their co-occurrences, right? That is basically, that's it for the GloVe, right? And we already have this. Of course we're gonna have this. We already have the weighting function anyway, right? So I think we are ready to make this model together. So the class GloVe, and then dot module, and sorry, and there are two functions we have to do, and that is that and that. It looks okay. Maybe if I do pass, it should have no errors. Okay, great. So what we're gonna do right here is basically very similar to what we have done previously, basically creating some embedding for our input. So the GloVe self.init, right? This is basically trying to initialize everything here so that we have all this function called forward, etc. Now we are creating self-embedding, self.embedding V, right? So this one basically I should just use center embedding equal to and then dot embedding vocab size and embed size, right? In that sense, we have to pass in this number, and we're gonna stick with 2 for the embedding size. So simply because we want to plot them nicely on the graph, and then further we're gonna do the same for outside word too. I'm gonna align them nicely here, and of course we also need the B here, right? So we're gonna also create some embedding for it, right? But notice that the size of it is not actually embedding. The size of one of it, this is actually 1. All right. So we're gonna say self.center bias, right? So center bias is basically I, right? So I is the center, and the J is basically the outside words. And then dot embedding vocab size, 1. All right. And then similarly for the outside bias, and then done embedding vocab size, 1. All right. So that is it, and we can actually check whether we are correct, right? So right here is vocab size, embed size, right? It multiply with embed size, vocab size, right? So that would give us vocab size and vocab size, right? And then we just add with vocab size, 1, right? I think there should be something we need to squeeze, right? To make sure that it can be added anyway later on. Okay. So let's do the forward function. So we can do center embeds equal to self.center embedding of the center word, All right, in that case, we have to send in the center word. And then we're going to have also the outside word. Right, and this is should be outside, similar to this one. All right, and then recall that this one is basically batch size 1 and embed size. Similarly to the batch size 1 and embed size. All right, and then what we have to do is creating the center bias too. Center bias equal to self.center bias, and we take in the center, and then we're gonna squeeze it. We're gonna squeeze 1. All right. In that case, if we squeeze 1, then it should be, there will be no longer 1, and there will be batch size, comma, vocab size, right? Maybe we can do some calculations outside to clearly see the shape. And then the next one is a target bias equal to equal to self dot outside bias, and this is outside squeeze 1. All right, and finally what we're going to do is we're going to first do this dot product. All right, and so and say inner product equal to outside embeds dot pmm center embeds not transposed 1 and 2, and then we're gonna squeeze this similarly to what we have done in the previous classes, right? So right here, this is a basically batch size dotted with, so we transpose 1 and 2, basically 2, 1 will be 1 and 2 will be switching places. So this will be embed size and 1, right? This will be equal to batch size 1 and 1, and we squeeze the 2. So we're gonna 2 means the second dimension here. So we're gonna have batch size 1, right? All right, and now we have the inner product, right? We can now doing the loss, right? And I guess this is this batch size comma 1 actually fits to this one, right? So that is also the reason why we now is I think is clear to me, and also that we designed to this shape simply because this will be, it will maps to this one, right? All right, so the loss function is nothing but so we will have the inner product, right? So this is the inner product, and we will be adding the center bias, adding the target bias, right? And we will be also minusing the COOC. And in that case, so we have to pass in the COOC and also the weighting. With the weighting, and of course, based on that, we can do torch.pow, and this will be the power of 2, right? Then we're gonna have this very nice power 2. Lastly, we need to multiply with this weighting, right? which is basically passing in here. So the weighting is that, right? And this weighting is not the weighting dict, right? But the weighting of only this center words, right? Which we already calculated earlier, right? Okay, great. So I think this should be it. All right. And we can return the loss. And now I think we can actually test our system a little bit. All right. So I think we have to initialize this model. So we're going to say model equal to GloVe. And what it needs is the vocab size and the embed size, right? And the vocab size is basically length of vocabs, length of vocab. Okay, just make sure I have this term. All right. Okay, 7. And we also have embed size, and that will be 2. And that we're going to have the model right now. And to test our network, we have to call this network, and it needs the center, outside, COOC, and weighting, right? Which actually we already have, right? So let me just go back into prepare data. Actually, we tested it, and we call this XY weighting, right? So we're gonna just copy this and run this. So we're gonna say model, and we're gonna pass in all this, and we're gonna get the loss, right? And hopefully there are no any problem. And it say that embedding must be tensor, and it's still the numpy. Okay, great. So that is obviously clear that we have to convert all this stuff into numpy. So we're going to say x equal to torch.long tensor x. And I think we don't need this because x is already a list. And we're going to do y equal to torch.long tensor y. And COC, COC is a float, right? So we're going to do float instead. So float tensor, COC, and then finally the weighting equal to torch dot. I think this is also float, right? Very clearly. Weighting, right? And I'm gonna do something just to make sure I don't lose the, in case I need. So I'm gonna say tensor. All right. So now what I'm gonna do here is make sure I'm using the tensor version. All right. And then now we get a very nice number, and of course I didn't run this clearly. And now I got a very nice loss. And let me take a look. And yep. All right. So I think we now have the nice loss. But I think I have to. So you can see that my loss is not actually okay, right? Because there's 2 numbers. So right here we have to do sum. All right. Sum. Okay, great. And actually this sum is basically referring to this across all the vocabs anyway, right? So I think this should be all right. So let me just make sure I stop here and clear all the outputs, restart run all, and now I should have only 1 number. Great. All right, so I think that is the neural network. I recommend that you guys try to type this by yourself, right? Because you learn more when you type, and try to print out each of them, take a look, right? And I guess the difficult part is like, why do I squeeze something like that? Maybe simply because the shape will work correctly. Otherwise, I don't think. I think as long as you understand this equation, then is quite good. It's not that difficult, right, to code this. Yeah. All right. So now we have the model, and I think we are ready to actually run the training, right? So I set the batch size to be 10, embedding size to be 2, and I think I'm going to change my model. I'm going to use the cross entropy loss, right? And the optimizer is Adam. And this time I have coded some time estimation. This is trivial. And now we're gonna start training. And we're gonna loop through the epochs, get some random batch, transform everything into tensor, and then zero grad, compute the loss, backward, and then step. All right. So we're gonna run this, and it seems like my loss is very low for some reason, right? And also the time is also very low. I guess the loss is very low simply because my data set is so small. But let us try to plot the embeddings. So these are all the vocabs I have, and I'm gonna do some. This is just some demonstration how I get the embedding, and I think this one, the name is center embedding, and this one should be outside embedding. All right, and so that would be the vector of it. But to actually get the word embedding, we take the average of the two embedding, the center word embedding and the outside word embedding. And now we can get the nice. This is basically the Y, right? But actually, I think we should print this one, and this is the nice embedding of this word. Now, similarly, we're going to create this function so that we can use this plot. And I think similarly, I need to change this to center embedding and outside embedding. All right. And this will be what we have right here. So you can see that animal, cat, and dog cluster in the left, right? At the same time, apple, fruit, and banana is quite on another side, right? So would this actually achieve what we want, right? That is the embedding that is close to one another, co-occurrence to one another, should appear more, should be closer to one another. At the same time, same for this one. Please ignore Ankh, right? Because Ankh is you don't really learn Ankh because Ankh it doesn't associate with one another, so it's randomly initialized, right? Next, we can show some cosine similarities, right? And we can take the cosine similarities between fruit and animal, right? In this case, they look that cat and animal is very big. At the same time, cat and fruit is very small, right? So this proves that actually cosine similarity help us. Without plotting, we can already know which word or even sentence in the future they are close to one another. And of course, cat is basically one. Right here, I'm just trying to write another the version of the cosine similarity using this SciPy called spatial distance cosine. This measure the cosine distance. So what you can do is just 1 minus it, and that would be the same number you get right here, right? All right, so I think that is the cosine similarity. So we're going to collapse this and also this one. And we can do some quick review, right? So that today what we have done is exploring this GloVe embedding. And we first load the data, we create a co-occurrence matrix, and then we prepare some trained data, basically a pairs of script. And then in the model, what we want trying to minimize is that the dot product of two words should not be should be very close to the log of the co-occurrence of the two words, right? That's it. And then we apply some weighting function, right? And then we sum across all the vocabs in the dictionary, right? And then we perform some training, we plot the embeddings, and then we do some cosine similarities. All right. So thank you very much for this tutorial.